So I'm going to share some of our recent works on periodically driven quantum many-body systems. But the focus is different from what you heard in the earlier talk by Krishnendu. So I'm mainly going to focus on looking engineering of novel phases like unconventional superconductivity at half filling, ferromagnetic half metallic phases, and in the second part of my talk, I will talk about periodically driven Sherrington Kirkpatrick model, where it is possible to realize a very robust discrete time crystal phase. So this audience actually doesn't need any introduction on periodically driven systems, but since I hope there are lots of students in the audience, so just to set the stage, let me say a few words about what all interesting can be done if you start driving a quantum many-body system periodically. So I will use the light and the periodic drivers in an interchangeable manner, although for some people it means very different things. So, when you drive a quantum many-body system periodically, you can induce many interesting phases. For example, it has been seen in experiments on topological insulators that one can induce anomalous quantum Hall effect on the 2D surface of a 3D topological insulator. One can induce anomalous Hall effect in graphene with the help of infrared light. And it's also possible to see superconducting-like behavior in non-superconducting phase of cuprates and other materials if you shine it with light, infrared light. Since this conference is mainly on ultra-cold atoms, let me also tell you that it is possible to engineer many interesting models which are otherwise not possible by shaking the optical lattices. And here are the examples. For example, one can engineer a Haldane model with ultra-cold fermions. And people have also realized Hofstadter Hamiltonian. And in context of the Fermi-Hubbard model that I will be talking about, it is possible to control spin exchange interactions. You can control the strength of these interactions. You can flip the sign of these interactions by shaking the optical lattices. And on a very different note, it's possible to generate very non-equilibrium phases of matter which are otherwise not possible. For example, discrete time crystals. So discrete time crystals are the phases of matter which break discrete time translational symmetry. It is extension of old idea by Wilczek, where he proposed that the time translational symmetry can be broken. And discrete time crystals have been seen experimentally in all sorts of platforms like trapped ions, diamond with nitrogen vacancy centers, and more recently in Rydberg atoms, in a finite array of Rydberg atoms. And there is also a proposal for observation of higher order discrete time crystals and fractional discrete time crystals in Rydberg systems. So with this brief background, let me come to the outline of my talk. So in the first part of my talk, I'm going to focus on periodically driven Hubbard model. I will show you how a sublattice dependent drive can help in overcoming can help in frustrating the antiferromagnetic order and stabilize the unconventional superconductivity even in a half-filled system. And in a slightly different regime of this same drive on the same system, one can also achieve ferromagnetic half-metallic phase. The crucial ingredients here are the dynamical freezing that can transform your system into strong correlations. I should actually use dynamical localization word here rather than dynamical freezing. And the drive induced higher range hoppings and staggered potentials, which are very important to induce this unconventional superconductivity. So this part of the work has been mainly done by a PhD student, Surya Shekhar Gusari, who is also there in the conference currently, and he also has put up a poster. So please see his poster for details of the work, because I will only be talking about the main results here. In the second part of my talk, I will discuss our work on periodically driven quantum Sherrington Kirkpatrick models. And I will demonstrate that although it's a system with all-to-all interactions, but because of the fact that the interactions themselves are random, it actually provides you an ideal platform to host a very robust discrete time crystal phase. This part of the work was mainly done by Arya Botra, who did his BSMS thesis in my supervision. And currently he is, he will be moving to Indiana State University for his PhD soon. So before I come to my work on periodically driven Hubbard model and unconventional superconductivity, let me just tell you, because many people in this audience may not be from the conventional material science and many body physics background. So why having unconventional superconductivity at half filling can be so interesting. Okay, so if you look at any material that is available to us, which has the hope of showing unconventional superconductivity, the parent compound in most of these materials is a Mott insulator, which has antiferromagnetic correlation. At most, it's a bad metal which has antiferromagnetic correlation. And in order to achieve superconductivity, you need to dope the system away from this commensurate filling, which also induces disorder because most of the time you have to do chemical doping. So in this work, I'm going to show you a non-equilibrium route to get superconducting phase without doping the Mott insulator. So at half filling in a Hubbard insulator, just by driving the system periodically with a very special drive, it is possible to have a D-wave superconducting phase. And I think it can be realized in ultra-cold atom systems, and it can have very interesting potential applications in quantum technology. Okay, so let me start with the first part of my talk on periodically driven Hubbard model. So here is the model. So H naught is the static model, which is basically a generic Hubbard model. T naught is the nearest neighbor hopping. U is the Hubbard interaction, and V naught is a staggered potential. So we will work with the staggered potential being 0 as well as finite in this talk. And then we have a sublattice dependent drive with an amplitude A and the drive frequency omega. And the drive has a phase difference of 2 phi on the two sublattices, A and B. So the overall Hamiltonian, the total Hamiltonian has a periodicity of 2 pi by omega. Now, this kind of periodic drive, which might look a bit complicated, but I think it can be simulated in optical lattices at least, which seems to be the ideal platform, because it should be, of course, there are experts sitting in the audience, so they can correct me if I'm wrong. I think it should be possible to shake the optical lattices along the two different sublattices, which I'm showing here as A and B, which are basically tilted at angle of 45 degree and 135 degree with respect to your x-axis. And if you keep a time lag between the two drives, then a time lag of delta t can actually provide you a phase difference of 2 phi between the two sublattice drives. So this way it should be possible to simulate it in real experiments. And as Krishnendu has already talked about, whenever you are talking about the periodically driven system, generic systems, if you are not very careful with the drive parameters, the system will just keep absorbing energy from the drive because we have not considered dissipation as such here. And eventually it will go to the infinite temperature state, but that's not what we are interested in. So we will be working in a special parameter regime, basically the high frequency regime, where the heating can be exponentially suppressed. Okay, so this has already been mentioned by Krishnendu, but I will just briefly mention that why the heating rate is exponentially suppressed in the drive frequency, because the heating rate is actually proportional to the dissipative part of this response function. If you try to look at the response of the field O within a linear response regime, and if you do some algebra, you can show that this response function will have commutators with respect to the Hamiltonian. And if your Hamiltonian is local, you can show that the norm is bounded from above with a term which is proportional to the characteristic energy of your system. And with this, you can show that the response function actually is bounded from above with an exponential form factor, exponential times the drive frequency. So if you increase the drive frequency, the time it takes to heat up is exponentially large in the drive frequency. And this has also been seen experimentally in context of periodically driven Fermi-Hubbard systems. And if you go beyond the linear response regime, By this I mean that along with the high frequency, you also have a large amplitude for the drive, then you can further suppress the heating. So we are going to basically work in the regime where the drive amplitude as well as the drive frequency are much larger than the characteristic energy scale of your system, keeping the ratio A by omega fixed. So under this parameter regime, one can do rotating wave approximation and absorb all the time dependence of the drive into the time dependence of the hopping term, as I have shown here. And now if I do the Magnus expansion and these terms up to 1 by omega order, this is the Floquet-Hamiltonian that we get. So as you can see that the nearest neighbor hopping that we had in the static model, it gets renormalized with this Bessel function. And when you hit the zero of the Bessel function, the effective hopping actually becomes zero. This is what is generally known as dynamical localization. But in this work, we will not be sitting exactly at the dynamical localization point because then the system will not have any dynamics. So the purpose is to work in the regime where the hopping is sufficiently suppressed such that it can transform your weakly interacting system into a strongly interacting system. So we stay a little away from the dynamical freezing point. Now, the more interesting things are the drive induces a staggered potential. So even if you start with a static system which does not have any staggered potential to start with, the drive induces a staggered potential. Drive also induces a second neighbor hopping, which is also staggered. It means it has different, the amplitude of this hopping, it has different signs on A and B sublattices. Drive also induces a third neighbor hopping, which I have shown here, between A sublattice and B sublattices. And very interestingly, there is a correlated hopping, which is a spin-dependent hopping. So this hopping basically prohibits doublons and holons to move from one sublattice to another sublattice. Now, just to give you an idea of what are the scales of these various terms which are induced by the drive. So we will be working in this range of the phase phi of the drive for a fixed value of drive amplitude and drive frequency. And as you can see that the nearest neighbor hopping has been sufficiently suppressed. As an effect of it, the on-site repulsion and the staggered potential is enhanced significantly. Twice of this term P prime effective gives you the second neighbor hopping, staggered hopping, and this is a correlated hopping. Now, so one thing to be noticed is that just by driving the system, we have entered into a very special strongly correlated regime where not only the Hubbard U is much, much greater than the kinetic energy, but also the effective staggered potential is much, much greater than the kinetic energy. Second thing is we have a finite next neighbor hopping, although it is staggered and it doesn't break the particle-hole symmetry, but it can still frustrate the antiferromagnetic order even at half filling. And this frustration of the antiferromagnetic order is crucial for stabilizing the superconductivity. And then T-correlated provides a spin-dependent hopping, as I already told you. So let's look at the kind of constraints we have in this Floquet-Hamiltonian because of this very special limits that both the U effective and the effective staggered potential are much, much larger than the kinetic energy. So now if you look at so in general, when you have a very large Hubbard potential compared to the kinetic energy and you're sitting at half filling, you should project out doublons and holons from your low energy Hilbert space. But here, holons are energetically expensive only on one of the sublattice and doublons are energetically expensive on the other sublattice. And because of this, you still have dynamics, like the hopping between the two sublattices is still allowed, although it is restricted. So this finite charge dynamics, which is present because of the large staggered potential along with the large Hubbard U, actually makes it possible to have some conducting phases in the system. So if you solve this Hamiltonian, this is a phase diagram that Surya has obtained, that as long as the drive phase phi is such that the effective second neighbor hopping cannot frustrate the antiferromagnetic order, your system remains an antiferromagnetic mod insulator. But eventually, the second neighbor hopping starts dominating. and it frustrates the antiferromagnetic order, and the system becomes a superconductor. So we looked for the superconductivity in various pairing channels, and we found that the D-wave superconductivity seems to be more stable. Throughout this superconducting and the Mott insulating phase, the system still has a density difference, with one sublattice having density more than 1 and the other sublattice having density less than 1. Now, this superconducting phase can be realized for a wide variety of drive frequencies and amplitudes, as shown here. So it seems to be very robust for all, as long as you are in the off-resonant driving regime, that the drive frequency is always larger than the characteristic energy scales of your static Hamiltonian. It's always possible to have this D-wave superconductivity in this driven system. The first set of phase diagram that I showed was for a specific value of the initial value of the staggered potential and the Hubbard interaction. But the superconducting phase is actually not so much dependent on the initial parameters. So you can vary the initial parameters a lot, and still you can see a broad superconducting phase. Even if you start with the system which does not have any staggered potential, the drive will induce the staggered potential and can provide you D-wave superconductivity, as I have shown here. So the system has a finite pairing amplitude on the nearest neighbor bond, even when you start with a zero staggered potential. With the same drive and the same Hamiltonian, if you start with a zero staggered potential and a slightly different ratio of the drive amplitude and the drive frequency, you can show that now the system will remain in an intermediate interaction regime rather than strongly interacting regime. And this system can actually host a stable ferrimagnetic half metallic phase. Now, both these phases that I'm talking about, So the superconducting phase that I have talked about and also the half metallic phases actually can have very interesting applications. For example, half metallic phase can have interesting applications in spintronics, because it can provide you a robust way of providing a spin-controlled transport. So if there are no questions on this part of the talk, I will go to the second part of my talk. So let me conclude the first part. So the summary is basically that if you start with a periodically driven Hubbard model on a bipartite lattice, and you have a spectral drive which also has this bipartite structure, in the high frequency and high amplitude regime, even at half filling, you can suppress antiferromagnetic order because of the drive-induced higher range hoppings, and you can basically achieve unconventional superconductivity at half filling. And if you work in a slightly different drive parameter regimes where you are away from the dynamical localization point, and the system can transform only into an intermediate interaction regime, the same system can host a ferrimagnetic half metallic phase. Now let me come to the second part of my talk, that is discrete time crystals. So all of us know what are crystals. And
there's a question.
Yeah.
Oh, very nice. One question is, how would you try to prepare the system? I mean, what is the temperature, or how small is the gap?
Sorry, can you repeat the question?
If you have this driven system, how would be the protocol to prepare the ground state, and how small is the gap to
the higher energy bands? Yeah. So actually, as a theorist, I have, for the time being, considered a single band Fermi-Hubbard model. But of course, in reality, even in cold atom systems, there are higher bands. So one needs to choose the drive frequency such that you don't transit, you don't go to the higher energy band. So the drive frequency should be such that it is higher than the energy scales of your Hamiltonian, but it should be smaller than the band gap. So I think it does lie in that regime if you look at some of the papers on Fermi-Hubbard models which have been periodically driven in cold atom setups. Have I
But the
answered your
temperature, I mean, even without the lowest band, do you think that the temperature to see the D wave is higher or smaller to the one that you get for the static model?
Okay. So I think the transition temperature, because your effective interactions are very large, right? Once you drive the system. In the static model, I'm starting with the interaction which is compared to the Hawk. So in the static system, there is no basically superconducting phase as such. And only when I
What set the temperature? Yes, you have to be much below.
Yes, I need to be below the transition temperature. That's true, but I think the estimate of the transition temperature is proportional to your uh, it's proportional to your density difference between the two sublattices times your effective spin exchange interaction in this calculation. And how much is the density difference between the two sublattices? Although the overall system is at half filling, there is a density difference between the two sublattices. Now, that difference depends on how much is the drive-induced staggered potential in your system. So we haven't actually tried to come up with the estimates of the transition temperatures as of now, but I think it's a very good question.
Yeah, there are no other questions.
Okay. Okay, so let me go to the second part of my talk, that is on discrete time crystals. So time crystals are actually phases of matter that can break time translational symmetry. And this idea was first proposed by Wilczek in 2012, although it was proved wrong very quickly. And we realized that it's not possible to have time translational symmetry breaking in systems with thermal equilibrium. But it can be possible to have such a breaking of time translational symmetry in out of equilibrium systems, for example, in periodically driven systems. So if you consider a periodically driven system which has a period capital T, it has a discrete time translational symmetry. And now if you look at certain observable O and in a time evolved state, and if it so happens that the time evolved expectation value of this observable O does not have the period of the Hamiltonian, but it has a periodicity n times capital T, where n is greater than 1, this is what we call discrete time crystal. This is the breaking of discrete time translational symmetry. If you don't like the terminology discrete time crystal, you can also think of it as an equivalent of charge density wave in real materials, which breaks the translational symmetry and has a periodicity different from the lattice translational symmetry. So this was the first experimental realization of DTC in disordered interacting spin chain long back in 2017, which told us some very important things, that it's important to have disorder, it's important to have interaction between the basic degrees of freedom in order to have a discrete time crystal phase. So you need interactions, you need disorder, and you also need isolation from the environment in order to see a robust discrete time crystal phase. Of course, it is possible to have free thermal DTC in absence of disorder, but in this part of my talk, I'm only going to focus on disordered systems, and that to disordered systems where the interactions are long range as well as random. So basically in the context of quantum Sherrington Kirkpatrick models, and I will show some evidences of DTC phase in this model. So this is the model that we basically talk about. So you have, these are the icing spins, and you have a coupling between all-to-all icing spins with Jij being random. So Jij are distributed from following Gaussian distribution with mean 0 and standard deviation J. And okay, this second part of the term depends on which driving protocol we are looking at. So we look at the system in two driving protocols. In the first driving protocol, in first part of the drive, we just flip all the spins. And in the second part of the drive, you time evolve it with respect to this Hamiltonian, where the quantum degree of freedom is added to this Sherrington Kirkpatrick model through this transverse field. So we look at the case of random transverse field as well as uniform transverse field. In the second driving protocol, the first part of the drive is same, that we just flip all the spins. And in the second part, when you evolve it with respect to the Hamiltonian, you don't have a transverse field, but you have a random hopping on the nearest neighbor sites. So there is a crucial difference between this part and this part. So first, let's look at the first one. So suppose I don't have a transverse field here in the H2, then of course it's a trivial DTC with a time period twice the period of the drive. So there's nothing important to see here. So it's very important to have this finite transverse field to see whether the DTC phase is robust or not. Now, in the second part, the system has a total SZ conservation. So there will be interesting aspects of it, like depending on the initial state, to which SZ sector the initial state belongs, you can have a different values of the DTC order parameter. So there is a parameter regime where you don't have any initial state dependence, but there is also a parameter regime where you see initial state dependent discrete time crystal phase just because of the conservation of the total SZ in this second driving protocol. So let's look at the first driving protocol. So we look at this autocorrelation function. So you start with a random product state in sigma z basis and let it undergo unit to time evolution with respect to your Floquet Hamiltonian. And as you can see here, that this is a case of the driving protocol 1, where we have a random transverse field in the second part of the drive. And these are the parameters. So you can clearly see period doubling oscillations, very robust period doubling oscillations for various set of initial states that we have tried. And if you do the Fourier transform of it, you see a subharmonic peak at half of the drive frequency. Now, one can also go to larger time scales and see that these period doubling oscillations actually do survive for very large time, even for all the initial states that we have tried. And now we can define the DTC order parameter as shown here. And this is the phase diagram that one can obtain from here in the HJ plane. So for a given strength of J, the DTC phase survives for a range of the transverse field, and this width in the transverse field increases as you increase the strength of your SK coupling. Now, these dashed lines are actually obtained from the delocalization to MBL transition in the Floquet Hamiltonian of the drive protocol 1. One is obtained from the average of the Van Neumann entanglement entropy, and the other one is obtained from the larger one is obtained from the peak position of the variance in the entanglement entropy. So of course there is a difference between the two because of the finite size system, but nonetheless you can see that most of the many-body localized phase is also the DTC phase. And once the system becomes ergodic, the DTC order melts. One can try to see, like, if you go to further larger time, whether this DTC order will survive or not. So we calculated, starting from a near state, the staggered magnetization as a function of time under a quantum quench, and you can see that the time scale over which the magnetization remains constant actually increases exponentially with the system size. Which shows that the DTC phase shown in this driving protocol 1 is actually very robust. Now, suppose you make this transverse field uniform, and what will you expect? So your system already has random interactions, so you would have expected it to be still non-ergodic and to give you a discrete time crystal phase. Well, it does show a discrete time crystal phase, but the width of the DTC phase is very narrow now compared to the case when the transverse field itself is random. So it's basically like a numerical experiment which tells us that along with the randomness in the interactions, randomness of transverse field also helps in stabilizing a broader DTC phase. And now we come to the second driving protocol, which is then along with the Sherrington Kirkpatrick model, you have random XY coupling on the nearest neighbor point. Now, if you just Just to remind you that if you have only the random XY coupling and no SK term, that actually has interesting history, because we know for fermions with random hopping, actually all the states except the state at equal to 0 is localized. So at equal to 0, you have diverging localization length, and the density of state also diverges. So now an interesting question is, now you have an interacting system because of this spin-spin interaction, and what kind of physics you will expect when you have the random XY hopping along with the Sherrington-Kirkpatrick model. So to be very honest, actually, when we did the delocalization to MBL analysis for this model, it was very confusing because the quantum quench dynamics shows that there is a transition at a finite value of this random field G. But if you look at the variance of the bipartite entanglement entropy or the level spacing ratio, we could not see any transition from delocalization to many-body localization. Also, we are restricted in the system size because of the Fluke nature. So I'm not going to show you any data on that MBL transition here, because I myself don't know whether where the transition is happening or whether it's happening or not. But at least the quench dynamics shows clearly that up to small values of G, the system is non-ergodic, and beyond that, I mean, the dynamics is almost frozen, and eventually the decay constant starts increasing as a function of G, and it should approach diffusive regime eventually. So this is the autocorrelation function as a function of time when you start with the initial random state again, and time evaluates with respect to this Floquet Hamiltonian. So this is for a very small value of G, I think 0.2 for J equal to true. And you see that for all the initial states that we have tried, you do see period doubling oscillations. Of course, here one should not look at the fully polarized states like ferromagnetic states, because your random XY term will not act on it. So, but other than those special states, we don't see any significant initial state dependence for small values of the random transverse field. You do see a clear subharmonic peak, and this is the range in which the DTC order parameter remains finite. So this is the phase diagram. But now if you go to larger values of this random spin flip terms, what you see is that there is a very clear initial state dependence in the autocorrelation function. You can also see that initial state dependence in the quantum crunch analysis of the Floquet Hamiltonian. So if you start with initial states in different total SZ sectors of the Hamiltonian, the decay constant with which the magnetization decays is actually has a very different behavior, as I've shown here. So this is for the nil state where the total SZ is 0. And these are for the states with a total SZ less than L by 2 or more than L by 2, and they have much lower dynamics. So now it's clear that when you go to larger values of G,
you have a couple of minutes.
Yeah. So when you go to larger values of G, there should be an initial state dependence reflected in your discrete time crystal phase also, and that's what we are seeing here, that already at T equal to 0.4, your discrete time crystal phase starts showing very strong initial state dependence. So this is the schematic phase diagram for the two driving protocols we have tried. In the case of transverse fields, there is a transition from discrete time crystal phase to the ergodic phase. In the case of random spin flip terms, there is a discrete time crystal phase. When you increase the strength of the random spin flip term, you do see a finite DTC order, but the value of the DTC order parameter changes depending on the initial state you are starting with. So you get some kind of pre-thermal or initial state dependent DTC phase, even in this disordered system, and eventually the system becomes ergodic. And finally, I would like to compare this SK model with the power law interacting system, where there is no randomness in the interactions. And you can see that there is a very strong initial state dependence for any strength of random transverse field that you can put in. For some of the initial state, there is no period doubling oscillations. And while for the same strength of the transverse field and the same strength of the interactions in the Sherrington-Kirkpatrick model, we saw a very robust DTC phase. So with this, I would like to conclude that the randomness among interactions And as well as long rangeness of the interactions actually can give you a very robust DTC phase. But having only long rangeness in the interactions and no randomness in the interactions is not sufficient to stabilize a DTC phase, as we have shown by comparing the case of uniform power law interactions and the Sherrington-Kirkpatrick model. And secondly, if you, rather than using the random transverse field, if you use random spin flip term, you have more flexibility of getting more than one kind of DTC phases because you have additional conserved quantities now. And by working in different conserved sectors, you can actually have different DTC phases. So with this, I would like to stop and thank you.
Yeah, questions?
Hello, ma'am.
Hi.
Question. Ma'am, initially you told that time symmetry is a discrete. If we take a time is continuous symmetric, then what happens? And which kind of result we consider now?
Well, there are models which show continuous time crystals also, and you need basically different models. So here in this talk, I have focused only on the system where the Hamiltonian has a discrete time translational symmetry, right? So if I have only discrete time translational symmetry, I can break only that.
Okay.
But there are systems where people have shown continuous time crystals also.
So basically, we get a single peak after Fourier transformation. The correlation.
You are asking what happens in the Fourier transform of the correlation function?
The correlation coefficient. After Fourier transformation, we get a single peak. This is basically related to discrete time symmetry.
Well, this is related to the drive frequency that you are working with, right?
Okay. Thank you.
Thank you. That's a very nice talk. Actually, you have talked about these DTC phases using the model you have described. And in that, you have talked about this disorder system, like disorderness is there. So like there are some other models are also there, like in central spin models, like LMG models. But those models, they don't have the disorder, right? But they still, from that model also, like people use those models to describe the DTC phases. So how do you see that the disorder?
Basically, what you need is some kind of non-ergodicity, right? Otherwise, your system will just heat up. We are not driving the system at a frequency which is very high, so there is nothing to prevent it from heating up unless you go to some non-ergodic regime, right?
Yes, yes.
I mean, that's my understanding. Maybe other people can add it too.
Okay. So another thing is like, as you have described that when you are increasing the G for the larger values of G, the phases, the DTC phases, that is basically initial state dependence it is showing.
Yes.
So that means the G has some optimum range where in between the DTC will come and then.
Yeah. So that's what I was showing in this phase diagram. That up to certain value of G, you don't see a significant dependence on the initial state. But if you cross that value, you start seeing a very significant initial state dependence. So actually, initial state dependence in this model, I think, is always there. It's just that it becomes much visible when you go to larger values of G.
Okay, but it does affect the robustness of that DTC phases, right? Like.
Yeah, of course. I mean, if it is not initial state independent, it's not a robust DTC.
Yeah. Okay. Thank you. Yeah.
Okay, so I think there are no other questions. So let's thank Arti again for a great talk.
Thank you. I will stop sharing.